CI 609. My name is Mark Delordo. This is my presentation on my final case study. The title is FOD Prevention in Aircraft Maintenance and All Aircraft Operating Environments. To guide you through my presentation, this is my outline slide. In the presentation, I'll be starting with a summary of my case study on FOD prevention. Then we will discuss the problem statement, giving two examples of FOD events. Then we'll be discussing the significance of the problem in terms of some different costs and damages and other variables I have. Then we'll be moving into the mitigation strategies, some things that are currently being done for FOD prevention methods. Then I have some recommendations to make for the industry and FOD prevention techniques. And then we have the conclusion with a summary and references. Okay, so to begin, we will start with the definition of FOD. It is foreign object damage, which is pretty much anything and everything that can damage an aircraft during its operation. It is estimated that FOD costs the international aerospace industry $13 billion in damages a year. In addition to the monetary cost, FOD threatens aviation safety and has contributed to the loss of a number of human lives. FOD can damage an aircraft in a various amount of ways, and it can take on a wide range of forms. Therefore, this case study will present places where FOD occurs, types of FOD, and discuss FOD mitigation strategies for all areas of aviation, including production, flight operations, and aircraft maintenance. Okay, so to begin with our problem statement of FOD, it was found that foreign objects have been a top recurring category of maintenance errors, and is mainly a human factor problem. Additionally, FOD is the direct cause of 8% of all airline incidents in the U.S. Because of its prevalence across the aviation industry, FOD prevention must be studied directly. Beginning with two examples, we'll discuss Air France Flight 4590. One of the biggest catastrophes caused by FOD was the crash of the Concorde in 2000 that killed 13 people. Minutes before the Concorde's departure, a Continental Airlines DC-10 dropped a titanium wear strip on their runway because of a poorly executed maintenance repair. The ill-fated Concorde then struck the metal, which caused a main landing gear tire to explode and in turn ruptured a fuel cell. The fuel leak started a massive fire across the left wing, causing both engines to fail, and then the Concorde collided into the ground 2 minutes after takeoff. The Continental Maintenance Air Department failed to complete an airworthy repair, which led to the FOD dropping from their aircraft and being left on the active runway. Continental Airlines was found responsible for the crash in court in order to pay Air France €1 million in addition to 70% of the compensation claims. It was revealed that an irregular repair had been made, not using an original equipment manufacturer's parts, OEM. Now, the second example is the Boeing KC-46 FOD issue. The Air Force has long awaited the deliveries of its new KC-46 Pegasus tanker aircraft from Boeing. However, twice this year they have stopped accepting them because of debris discovered in several airplanes, including loose tools and unwanted materials. 2 times in March, Air Force halted acceptance of the aircraft because of the FOD discoveries. Not surprisingly, this dealt a huge blow to Boeing's reputation, business, and production rate. As much as any airliner, military aircraft are sensitive to FOD incursions, and the Air Force did not take lightly to Boeing's failures. They began a Level 3 complaint against Boeing, which requires a major overhaul of the organization's processes and will cost Boeing millions in readdressing their operations. Because of these two problems and the prevalence of FOD across the aviation maintenance industry, this case study will begin discussing recommendations and mitigation strategies. In addition to the examples given in the problem statement, here are some of the additional costs of FOD. We've already discussed that it's cost hundreds their lives and millions in damage. Additionally, it costs maintenance and labor hours, flight delays, cancellations, lost revenue, and overtime for employees. It can cause engine damage, tire damage, loss of fuel efficiency, and damage to runways and support equipment. Here are some of the mitigation strategies that were discussed in my case study. First one is designating 5 critical areas. This can benefit aerospace production and aviation maintenance departments by telling the workers and everyone involved how sensitive certain areas of an aircraft are to FOD and keeping it out of those areas. Next, doing FOD walks is a critical action of FOD prevention, which can help maintenance and flight operations, keeping FOD off runways and doing personnel sweeps, picking up debris off of runways. Also, there's FOD detection on runways now, which would have helped prevent the Concorde tragedy that was discussed. There's these specialized radars that can detect FOD on runways and alert airport operations personnel to remove the FOD. And there's also tool control programs for aircraft maintenance with shadowed toolbox and tool control and accountability and inspections to ensure that tools do not become FOD and left on airplanes. From the research collected in this case study, I've come up with 2 recommendations. The first is training. A thorough FOD indoctrination course should be given to all new hires in a maintenance department, because while most technicians have completed an airframe and power plant course or certification, it cannot be assumed that they are FOD experts. Additionally, recurring training shall be given at least annually to all employees to help emphasize the maintenance department's focus on FOD elimination and prevention. Next, all companies in aerospace production, operations, and maintenance should invest in technology for FOD prevention. Like the radar detection systems we've already discussed, e-drills have now been invented that can eliminate FOD during drilling operations. Perfect Point has now produced a drill that can remove, install fasteners, and drill without producing any FOD. It captures its own shavings and dramatically reduces the amount of FOD. Therefore, from these examples, technological advances can greatly reduce FOD occurrences. In conclusion, the goal of this case study was to raise FOD awareness through education of historical examples, discuss the significance of FOD, detail mitigation strategies, and provide recommendations for FOD prevention and aviation maintenance. Because of the severe consequences of costs and FOD, there is a number of brilliant technologies focused on FOD prevention and detection for an aviation maintenance department to utilize in its operations. These final few slides are the list of references I used throughout the case study. Thank you very much for listening and have a nice day.